I guess all about.
You don't need to, I mean, I'm Toby Isaac. All right. Okay, so we've got a feature that's very close to getting merged into main called TaoTerm that I want to tell everyone about. Okay, so if you think about solving a linear system with PETSc, what does the interface for KSP solve look like? KSP solve, the KSP has a matrix A, but each time you call KSP solve, you specify a separate B and a separate X. So these separate objects, I think, do a good job of breaking down the interface into appropriate parts. We've got the problem A. It can be shared between multiple solvers. We've got problem data B, but the problem is the combination of A and B, but at least for the way PETSc works, we don't change the solver on B, right? That's the problem instance, but it doesn't really change the type of thing that we do. And those are separate from the solution algorithm itself. It can inspect A, define structure that can be exploited. Okay, so let's take a look at the status quo with Tao, the optimization solver methods. So with Tao, the general approach is you create a Tao, you set the objective and the gradient into the Tao itself, set anything else you need to compute the Hessian, and now you call Tao solve where Tao is the only argument. So there's no separation in the status quo between the problem, so like matrix A, instance data, something like a vector B, and the solution algorithm. It's all in the Tao. And the general interface is all through callbacks. So the thing to ask yourself is, what would KSP not be able to do if the only implementation of mat was mat shell? You couldn't get elements on the diagonal. You couldn't try to get any kind of other data out of it, right? That would limit the types of options that are available. So to expand the types of things that we can do in Tao, we are introducing something called TaoTerm. So it's a parametric, real-valued function. It's a PETSc object that you can hold, just like a mat, right? So it's going to have an interface that looks a lot like the function querying things that you do in Tao right now. But it's just for the term. It doesn't contain solution algorithms. So TaoTerm objective gives you F. TaoTerm gradient gives you the gradient with respect to X. And TaoTerm Hessian will give you the second gradient. It's parametric for reasons that I'll show shortly. But if your function isn't parametric, P is equal to null. It's going to come with some built-in implementations. So shell is just going to take callbacks like we do already. But there are some building blocks that people use all the time that we're going to make available for you. Half L2 squared, L1, quadratic, and very important for a lot of algorithms we want to look at, TaoTerm sum. So it's going to give you a bunch of scaled terms. And very critically, we're going to have mapped terms. So you can have that X gets through some sort of a transformation before it goes into quadratic or goes into L1 or something like that. And of course, we also want to give other building block convex functions like logit or KL divergence that are going to be particularly relevant to like regression problems, which we're going to hear about from Richard later on. Okay, so let's say you want to do a compressed sensing example. It's going to, let's say you've already done PETSc code to compute or define the matrix A, the matrix D, the vector B. It's TaoTerm create of half L2 squared. You set the basic, the first term in Tao as the using mapped syntax like we had in TaoTerm sum. So we're adding in 1 times 1/2 L2 squared applied to A of X with data B. And there's that parameter, right? So it's important for these built-in functions to be parametric to allow this type of functionality. And then we add an L1 term with the dictionary matrix D. And now if you do this and you run this, you ought to be able to just do Tao type NLS, and it'll give you Newton's method. It'll give you a smooth version of L1. And you can just do ADMM, which will just treat the terms separately. It will work just right out of the box. You can do things like change the scaling on your terms from the command line, so if you want to play around with the regularization. And a feature that the exact syntax is kind of still in flux, you'll also, from the command line, be able to just add basic regularization blocks to objective functions. So you just decide, I want to add a little bit of L1 to this. You don't have to change your code. If you like your old interface, you can keep it. So if you still call tau set objective and gradient, there is kind of a special tau term on the inside that receives the old syntax for specifying things that way, so the old code is still going to work. And once we have these things that we can hold and think of and analyze and inspect, we can start to do things beyond gradients. So a big thing that is important to convex optimization methods for things that are not smooth but are convex are proximal maps, for instance. So if I've got f and it's convex but not smooth, I can still have this map. It is an exact one-to-one map for every y. There's going to be a unique solution x. So this is very important. And so we will be able to attach this type of information to a tau term, and it makes it easier to implement proximal methods. And so if you think about it, you'll see, hey, this is a minimization problem, especially if alpha is equal to 0, you're just minimizing f. Why isn't this just a tau? And kind of the way you want to think about it is we have KSP solve and we have MAT solve, right? KSP solve is iterative and general purpose. MAT solve is direct and implementation dependent. It's the same thing with proximal maps. So tau solve is going to help you solve anything, but our built-in bits and pieces are going to have exact proximal maps that we'll be able to compute exactly. So all these things are going to expand the types of optimization algorithms we can do. I just want to kind of show you the output of a ADMM example. So ADMM, if we take a look at problems of the form like f of ax plus g of bx, you can transform this into a constrained optimization problem where you use different variables for the f and g terms in a few different ways. You could do f of ax plus g of by, where we just want x is equal to y. We could do f of z plus g of by, where we want z is equal to ay. And we could also do f of ax plus g of z, where z is equal to bx. These are all different ways that you could try to set up, and there are going to be advantages or disadvantages for each of them. And for using TaoTerm, I can now, for instance, run ADMM without changing the user code, choose the type of version that I do. So I've got a version where I do tau ADMM, and it says I'm keeping the map D on the inside, but I'm pulling the map C out in this version. And then if I run the same code using different options, I can run it as keep the C map on the inside and pull the D map out, that kind of stuff. So it's going to really increase the kind of flexible composition of components in tau. So look for that to arrive soon, and look for your coffee to arrive outside right now. Okay, do you want to say anything? Or?
I want a question. In the interface, you had grad x. Are you also going to have a grad p in the TaoTerm?
So are we going to do things like gradient with respect to the parameter? I think that it does make sense eventually if we start doing things like outer loop stuff. But you know, we're keeping it to basic principles right now. Yeah. All right, thanks everyone. That's going to conclude our first session. We'll meet back at 11 to start the second session of the morning. Thanks, y'all.